Autonomous AI agents are incredibly capable, but that autonomy becomes a severe vulnerability when they execute unmonitored API calls. Without strict oversight, an agent tasked with a simple read operation might hallucinate a command and breach rigid enterprise networks. To solve this, we use Auth0. This library enforces constitutional token governance, dictating exactly what an AI agent is allowed to do before it even touches an API. We are going to build a role-based, pre-flight validated system. By the end of this setup, you will have automated step-up authentication for sensitive actions and an immutable audit log tracking every single token request. Before we begin, verify your environment. You need Python 3.11 or higher, an active Auth0 machine-to-machine application, and the client ID, secret, and domain set as environment variables. Moving governance out of the AI's internal prompting and into an external, static constitution changes how we secure these systems. We move away from reactive filtering and rely instead on a fixed policy that validates every request before the agent can even attempt a network connection. Step 1 is to initialize our workspace. Open your terminal and install the base library using pip install acgs auth0. Since we are going to integrate this directly into LangChain tools, append the bracketed LangChain tag to the install command to grab the necessary extensions. Next, create a new file named constitution.yaml in your root directory. This document will act as the absolute source of truth for our access policies. Our structure starts with a token vault key, branching into executive and implementer roles. The executive gets restricted read-only permissions, like read user. The implementer requires destructive access, so we grant repo write. Because write access is dangerous, we flag it under high-risk scopes to trigger strict oversight. Pay close attention to formatting. A common failure point is misaligning the indentation under the token vault header, which will cause the parser to fail entirely. Codifying these limits in a strict file architecture takes access control away from the AI's probabilistic reasoning. The agent no longer decides what is safe. The hard boundary of the YAML file does. Now let's move into our Python environment. Import the library and instantiate the constitutional token vault client, pointing it directly to our new YAML file. We will simulate a continuous integration agent by constructing a token vault request. We assign this request the executive role and ask for standard GitHub read scopes. This diagram illustrates how the validate function operates as a localized pre-flight verification system. Instead of pinging an external server, it evaluates the request by comparing it directly against the local YAML constitution, completely isolated from the Auth0 network. Running this code prints the validation object, showing allowed read scopes and no denied scopes. If the agent instead requests repo write, the local vault immediately blocks the attempt. The Auth0 network node is never engaged. Halting unauthorized network traffic locally ensures credentials are never exposed for a bad request. The API connection is completely denied before it ever begins. To apply this framework directly to LangChain, we use the @with constitutional token vault wrapper to decorate our agent's tools. The decorator explicitly encapsulates the tool function. It references our policy and specifies scopes, clamping down on execution before the function logic can start. Inside the decorated function body, we must call getTokenVaultCredentials. This retrieves the access tokens securely injected by the vault. Be careful with your execution context. If you attempt to call the credential function anywhere outside of a properly decorated tool, the system will instantly throw a runtime failure. When an agent like our implementer requests a high-risk scope, the system triggers client-initiated back-channel authentication, or CIBA. It pauses the autonomous execution flow entirely, waiting for an external human to verify and approve the action. This automated CIBA trigger allows agents to operate at autonomous speeds for standard tasks, while enforcing hard-coded mandatory human oversight for critical infrastructure changes. With our tools securely wrapped, we can extract the historical auditing data using the token audit log class. You do not need to log these events manually. The vault and the decorator automatically append every granted, denied, and step-up event directly to an immutable record. We can iterate through these entries to extract specific details, pulling out the outcome, the agent ID, and the exact requested scopes for every single operation. This table shows the returned system log entries. Every single entry features a constitutional _hash property. This repeating alphanumeric string represents the exact version of the YAML policy that was in effect at the moment the access was requested. Permanently tying every AI action to a specific cryptographic hash eliminates ambiguity. It provides absolute proof of exactly which rules authorize the access, achieving a verifiable standard of zero trust accountability.